NENOMATICA, where mathematics meets YouTube excellence. Exponential equations. Welcome to this math tutorial. Let's solve an exponential equation example. Let's start solving this problem. We need to find the value of x in the exponential equation 3 to the power of x plus 3 to the power of x plus 2 plus 3 to the power of x plus 4 equals 819. First, let's rewrite the expression to help us factor out common terms. I'll use the exponent property that a to the power m times a to the power n equals a to the power m plus n. So 3 to the power x plus 2 can be written as 3 to the power x times 3 squared, and 3 to the power x plus 4 can be written as 3 to the power x times 3 to the power 4. Now I can see that all three terms contain 3 to the power x as a common factor. Let's factor this out. Let's evaluate the values in the parentheses. 3 squared equals 9, and 3 to the power 4 equals 81. Now we add the numbers inside the parentheses. 1 plus 9 plus 81 gives us 91. To isolate 3 to the power x, we need to divide both sides by 91. Let's simplify the fraction on the right side. 819 divided by 91 equals 9. Now, we can write 9 as a power of 3. 9 equals 3 squared. When we have the same base on both sides of an equation, we can set the exponents equal to each other. So x equals 2. Therefore, our solution is x equals 2. Let's verify this answer by substituting x equals 2 back into the original equation. When x equals 2, 3 to the power of x equals 9, 3 to the power of x plus 2 equals 81, and 3 to the power of x plus 4 equals 729. 9 plus 81 plus 729 equals 819, which matches our right side. So our answer is correct. Let's solve the exponential equation step by step. Our example is 5 raised to the power of x plus 2 minus 5 raised to the power of x minus 1 equals 620. First, we'll rewrite each term using the exponent rule that says a to the power of m times a to the power of n equals a to the power of m plus n. For the first term, we get 5 to the power of x times 5 squared. For the second term, we get 5 to the power of x times 5 to the negative 1 power. Now, we can factor out the common term 5 to the power of x from both expressions. This gives us 5 to the power of x times open parenthesis 5 squared minus 5 to the power of negative 1 close parenthesis equals 620. Next, let's calculate the values inside the parentheses. 5 squared is 25, and 5 to the negative 1 power is 1 over 5. Now, we need to simplify the expression inside the parentheses. To do this, we need a common denominator. We get 5 to the power of x times 124 over 5 equals 620. To isolate 5 to the power of x, we need to divide both sides by 124 over 5. This gives us 5 to the power of x equals 620 times 5 divided by 124. Now, let's simplify the right side of our equation. 620 times 5 divided by 124 equals 25. We can rewrite 25 as a power of 5. 25 equals 5 squared. Finally, since we have the same base on both sides, we can set the exponents equal to each other. Therefore, x equals 2. Remember the rule. When two expressions with the same base are equal, their exponents must also be equal. So, our solution to the original exponential equation 5 to the power of x plus 2 minus 5 to the power of x minus 1 equals 620 is x equals 2. Let's verify this by substituting x equals 2 back into our original equation. Welcome to today's mathematics video. We'll be solving an exponential equation with square roots that requires careful attention to domains and properties of exponents. Let's look at our example problem. We need to solve the equation. The square root of 5 minus x times 3 raised to the power of x squared minus 7.2x plus 3.9 minus 9 times the square root of 3 equals 0. First, we need to check the domain constraint for the square root. Since we have square root of 5 minus x, we need 5 minus x to be greater than or equal to 0. This means x must be less than or equal to 5. Now, we need to solve this equation. We have a product equal to 0, which means either the square root of 5 minus x equals 0 or the expression in parentheses equals 0. Let's first consider when the square root equals 0. This happens when 5 minus x equals 0, which gives us x equals 5. Next, we consider when the expression in parentheses equals 0. That is, when 3 raised to the power of x squared minus 7.2x plus 3.9 minus 9 times the square root of 3 equals 0. To solve this, we'll convert 9 times the square root of 3 to a power of 3. 9 is 3 squared, and the square root of 3 is 3 to the power of 1/2. So 9 times the square root of 3 is equal to 3 to the power of 5/2. Since we have the same base, 3, with different exponents, and their difference equals 0, these powers must be equal. This means the exponent x squared minus 7.2x plus 3.9 must equal 5/2. Let's rearrange this to the standard form of a quadratic equation. We'll subtract 5/2 from both sides to get x squared minus 7.2x plus 3.9 minus 5/2 equals 0. Now, let's simplify the constant terms. 3.9 minus 5/2 equals 3.9 minus 2.5, which gives us 1.4. Now, we need to solve this quadratic equation. Using the quadratic formula, we find that x equals 7 or x equals 1/5. Remember our domain constraint, though x must be less than or equal to 5. Since 7 is greater than 5, we need to check if it's a valid solution by plugging it back into the original equation. Actually, we can directly rule it out because it violates our domain constraint. 1/5, on the other hand, is less than 5, so it satisfies our domain constraint. Therefore, we have two potential solutions, x equals 5 from our first case, and x equals 1/5 from our second case. Both satisfy our domain constraint, so our solution set D consists of the values 1/5 and 5. Let's solve the following exponential equation. First, let's note that 2 to the power of 10 equals 1024. Multiplying both sides by 2, we get 2 to the power of 11 equals 2048. Next, we restate our original equation, and note that 2 to the power of 11 equals 2048. Now, we can substitute 2 to the power of 11 for 2048 in the exponent of our equation. Let's rewrite this further. We know that 2 to the power of 11 equals 2 times 2 to the power of 10. Next, we can express 2 times 2 to the power of 10 as 2 to the power of 1 plus 10. Simplifying the exponent, we get 2 to the power of 11. We can further rewrite 2 to the power of 11 as 2 to the power of 3 times 2 to the power of 8. Using the power rule, that a to the power of b, all raised to the power of c, equals a to the power of b times c, we can rewrite our equation as 2 to the power of 8, all raised to the power of 2 to the power of 8. Comparing with our original equation, x to the power of x equals 2 to the power of 2048. We can see that x must equal 2 to the power of 8. Finally, 2 to the power of 8 equals 256. Therefore, x equals 256. We have successfully solved the exponential equation, following the exact procedure shown in the original problem. The solution is that x equals 256. Welcome to our mathematics video. Today we'll solve an interesting exponential equation. Let's look at our example. Our problem is to solve the exponential equation x raised to the x power equals 2 raised to the power of 2048. To solve this equation, we'll try a clever substitution. Let's assume that x equals 2 raised to the power of n, where n is some number we need to find. Now, let's substitute this expression into our original equation. We replace x with 2 to the power of n everywhere in the equation. Next, we apply the exponent rule, which states that when we have a number with an exponent raised to another power, we multiply the exponents. So 2 to the power of n raised to the power of 2 to the power of n equals 2 to the power of n times 2 to the power of n. Since the bases are the same on both sides of the equation, the exponents must be equal. Therefore, n times 2 to the power of n equals 2048. To simplify further, let's express 2048 as a power of 2. Since 2048 equals 2 raised to the power of 11, we can rewrite our equation. Now, let's isolate n. We divide both sides by 2 to the power of n. Using the rule for dividing exponentials with the same base, we can simplify the right side to 2 raised to the power of 11 minus n. Now we have the equation n equals 2 to the power of 11 minus n. This is a special type of equation where n appears on both sides. Let's try n equals 8 and see if it works. Since n equals 8 satisfies our equation, we can now find x. Since x equals 2 to the power of n, we have x equals 2 to the power of 8. Let's solve this exponential equation step by step. First, let's understand what we're working with. In this equation, we have x times the square root of x on the left side, and the square root of x raised to the power of x on the right side. We'll assume that x is greater than 0 to ensure all terms are well defined. To solve this equation, we'll rewrite both sides using exponent notation. On the left side, x can be written as x to the power of 1, and the square root of x can be written as x to the power of 1/2. Now, we can use the laws of exponents to simplify the left side. When multiplying terms with the same base, we add the exponents. So x to the power of 1 times x to the power of 1/2 equals x to the power of 1 plus 1/2, which is 3/2. Let's further simplify the left side. 1 plus 1/2 equals 3/2. Next, let's simplify the right side of our equation. When raising a power to another power, we multiply the exponents. So the square root of x, which is x to the power of 1/2, raised to the power of x, equals x to the power of 1/2 times x, which is x to the power of x over 2. Now, we have a simplified equation x to the power of 3/2 equals x to the power of x over 2. Since x is greater than 0, the bases are the same, so the exponents must be equal. Let's solve for x by multiplying both sides by 2. Therefore, x equals 3 is our solution. However, as noted in the original problem, x equals 1 is also a solution. We can verify this by substituting x equals 1 into the original equation. In summary, we found that x equals 3 and x equals 1 are both solutions to the equation x times the square root of x equals the square root of x raised to the power of x. Let's examine our example. We have the equation x raised to the power of x equals x, where x is not equal to 0. To solve this equation, we need to isolate the variable. Let's start by dividing both sides by x. Since we're given that x is not equal to 0, this step is valid. Now, we'll apply the exponent rule that states, when we divide a number raised to a power by the same number, we can subtract the exponents. In this case, we get x raised to the power of x minus 1 equals 1. Now, we need to find the values of x that satisfy the equation x raised to the power of x minus 1 equals 1. This means either the base equals 1 or the exponent equals 0, or we have a special case. Let's examine these cases one by one. In the first case, if x equals 1, then we have 1 raised to any power equals 1, which is true. So x equals 1 is a solution. In the second case, if x equals -1, we need the exponent x minus 1 to be an even integer for the equation to be true. When x equals -1, the exponent becomes -1 minus 1, which is -2. Since -2 is an even integer, x equals -1 is also a solution. For the third case, x minus 1 equals 0 implies that x equals 1. But we've already counted this solution in our first case, so we don't need to add it again. Therefore, the solutions to our equation x raised to the power of x equals x, where x is not equal to 0, are x equals 1 and x equals -1. Welcome to this math tutorial. Let's solve an exponential equation step by step. We need to solve for x in this exponential equation. Let's start by rewriting 5 to the power of x plus 1 as 5 to the power of x times 5. Now, I'll factor out 5 to the power of x from both terms on the left side. Let's simplify inside the parentheses. 1 plus 5 equals 6. Now, I'll divide both sides of the equation by 6. 6 divided by 6 equals 1. Any number raised to the power of 0 equals 1, so we can rewrite 1 as 5 to the power of 0. Since the bases are the same on both sides, the exponents must be equal. Therefore, x equals 0. Therefore, the solution to the equation 5 to the power of x plus 5 to the power of x plus 1 equals 6 is x equals 0. We can verify this by substituting x equals 0 back into the original equation. The key insight in this problem is that when we have the same base with different exponents, and when we can isolate the exponential expression on one side, we can set the exponents equal to each other. Let's look at this example. We need to solve the equation. 5 raised to the power of 2x plus 2 times 2 raised to the power of 2x equals 0.0025. Let's start by rewriting our equation. First, we'll use the exponent law to split the first term, 5 raised to the power of 2x plus 2, as 5 raised to 2x times 5 squared. Then we'll rewrite 0.0025 as the fraction 25 divided by 10,000. Next, let's rewrite 10,000 as 10 to the fourth power in the denominator. Now, let's simplify the left side. We know that 5 squared equals 25, so we can pull that out as a coefficient. Then we can combine the remaining terms by noticing that 5 times 2 equals 10, and according to the laws of exponents, when we multiply terms with the same exponent, we multiply the bases. So we get 25 times 10 to the power of 2x on the left side. On the right side, we can rewrite 25 divided by 10 to the fourth as 25 times 10 to the power of negative 4. Since both sides have a common factor of 25, we can divide both sides by 25 to simplify further. We now have 10 raised to the power of 2x equals 10 raised to the power of negative 4. When we have the same base on both sides of an equation, the exponents must be equal. Therefore, 2x equals negative 4. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.